Hello everyone. Welcome back to my course Aerospace Engineering, Avionics and Aerospace Systems. In this video, we will talk about the general description of engine systems. This is going to be our last unit of this course. Also, I would be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. ATA chapters. The ATA chapters for engine systems are part of the ATA 100 specification, a standard used in aviation to organize technical documentation. For engine-related systems, the chapters are grouped in the 70 series. Here's a breakdown. ATA Chapter 70 Standard Practices Engine. This chapter covers general maintenance procedures that apply to engines, such as safety precautions, cleaning, and basic practices for working on engine systems. ATA Chapter 71 Power Plant focuses on the installation and removal of the entire engine, power plant, including mounts and nacelles. It deals with how the engine is attached to the aircraft. ATA Chapter 72 Engine. The most detailed engine chapter, it covers internal engine components and assemblies like compressors, turbines, fans, combustion sections, and overhauls. This is essentially the core engine content. ATA Chapter 73 Engine Fuel and Control covers the fuel delivery and control systems specific to the engine. This includes components such as fuel pumps, fuel control units, and electronic systems like FADEC. ATA Chapter 74 Ignition describes the ignition systems used to start the combustion process in the engine. Components include igniters, exciter units, and wiring. ATA Chapter 75 Air involves systems that handle compressed air taken from the engine, bleed air, for use in anti-ice, cabin pressurization, and other aircraft functions. ATA Chapter 76 Engine Controls relates to mechanical and electronic control systems such as throttle levers, linkages, and actuator controls that influence engine operation. ATA Chapter 77 Engine Indicating describes the sensors and indicators that provide feedback on engine performance like N1, N2, EGT, oil pressure, and temperature gauges. ATA Chapter 78 Exhaust deals with the exhaust system, including components that handle or redirect engine exhaust gases, thrust reversers, and noise suppression. ATA Chapter 79 Oil covers the engine lubrication system, including oil pumps, filters, coolers, and lines that ensure proper lubrication of internal engine parts. Purpose and function of engine systems. The engine system is one of the most vital components of an aircraft, serving as the heart of its propulsion and a major source of power for various onboard systems. Fundamentally, the primary purpose of an aircraft engine is to generate thrust, which propels the aircraft forward through the atmosphere. This forward motion, combined with the aerodynamic shape of the wings, enables the aircraft to generate lift and sustain flight. However, beyond just producing thrust, modern aircraft engines serve multiple critical functions. They are responsible for generating electrical power through engine-driven generators, which power cockpit avionics, lighting, flight instruments, and onboard entertainment systems. The engine system also provides hydraulic power to operate control surfaces, landing gear, brakes, and other actuators. Furthermore, High-pressure bleed air extracted from the engine compressor stages is used in environmental control systems, which manage cabin pressurization and temperature regulation. This same bleed air may also be routed to anti-ice systems to prevent the accumulation of ice on wings, engine inlets, and other vital surfaces during flight through icing conditions. In addition, engine systems incorporate sophisticated control and monitoring functions. Modern engines are equipped with FADEC, Full Authority Digital Engine Control, units which manage all aspects of engine performance, including fuel metering, temperature regulation, and response to pilot inputs. This not only enhances performance and efficiency, but also improves safety and reduces pilot workload. Overview of engine integration with aircraft. Integrating the engine system into the overall aircraft design requires careful attention to structural, aerodynamic, and operational considerations. Engine placement varies depending on the type and purpose of the aircraft. In many commercial jets, engines are mounted on pylons beneath the wings, which allows for better aerodynamic performance, ease of maintenance, and increased safety in the event of an engine fire. Other configurations, such as rear-mounted engines on business jets or tail-mounted engines on some military aircraft, are chosen based on design priorities such as noise reduction, ground clearance, or center of gravity balance. The physical integration of the engine involves mounting it within a nacelle, a streamlined housing that reduces aerodynamic drag and provides protection against environmental exposure. The nacelle often includes components such as thrust reversers, acoustic linings for noise reduction, and fire containment features. Structural pylons attach the nacelle to the aircraft frame and are designed to handle the engine's weight, vibrations, and thrust loads. You can also learn more about aircraft structure from my other course named Aerospace Engineering, Aerodynamics, and Structures. You can find this course in my profile and dive deep into the aerospace structures. The engine system is also integrated with the aircraft's fuel delivery system. Fuel tanks, typically located in the wings or fuselage, are connected to the engine through a network of pumps, valves, and sensors. This system ensures consistent fuel supply under varying flight conditions, including different altitudes, attitudes, and during maneuvers. In addition to fuel integration, the engine is connected to the aircraft's electrical, hydraulic, and pneumatic systems. Generators mounted on the engine shaft produce electricity as the engine runs. Hydraulic pumps use the engine's mechanical rotation to power flight control systems. Meanwhile, bleed air ducts carry high-pressure air from the engine's compressor stages to pressurize the cabin and power other pneumatic devices. Safety integration is also a priority. Fire detection systems monitor the engine compartment for abnormal temperatures, and fire suppression systems are installed to extinguish fires using halon or other extinguishing agents in emergency situations. Basic engine operation principles. Understanding the basic operation of aircraft engines requires examining the two main types used in aviation: piston engines and gas turbine engines. Piston engines, also known as reciprocating engines, operate on a principle similar to automotive engines. They rely on the internal combustion process, where a mixture of air and fuel is drawn into a cylinder, compressed by a piston, ignited by a spark plug, and then expelled after combustion. The combustion forces drive a crankshaft, which in turn rotates a propeller mounted at the front of the engine. Piston engines typically operate on a four-stroke cycle: intake, compression, power, and exhaust. These engines are most commonly used in small general aviation aircraft due to their simplicity and lower cost of operation. In contrast, gas turbine engines are the standard power plants for most modern commercial, military, and business aircraft. The operation of a gas turbine engine is based on the Brayton cycle, which involves continuous intake, compression, combustion, and exhaust. Air is drawn into the engine through an intake and compressed by multiple stages of axial or centrifugal compressors. The high-pressure air is then directed into a combustion chamber, where it is mixed with fuel and ignited. The resulting high temperature, high-pressure gases expand rapidly and pass through a series of turbine blades. These turbines extract energy from the exhaust gases to drive the compressors at the front of the engine, completing the cycle. The remaining exhaust gases are expelled at high speed through a nozzle at the rear of the engine, producing the thrust necessary to propel the aircraft forward. This process follows Newton's third law of motion. For every action, there is an equal and opposite reaction. Types of gas turbine engines. There are several types of gas turbine engines used in aviation, each suited to specific roles. Turbojet engines produce all of their thrust from the exhaust jet and are mainly used in military aircraft due to their high-speed capabilities. Turbofan engines, which are the most common in commercial aviation, use a large fan at the front of the engine to move a significant volume of air around the core. This bypass air increases thrust while improving fuel efficiency and reducing noise. Turboprop engines use a turbine to drive a propeller, combining the high-speed capability of turbines with the efficiency of propellers at lower speeds. Turboshaft engines, commonly used in helicopters, deliver rotational energy to a drive shaft rather than producing thrust directly. These engines operate under precise control systems, and their performance is continuously monitored and adjusted by onboard computers to ensure optimal efficiency, safety, and reliability throughout all phases of flight. Also, if you want to have extensive knowledge about aerospace engines, make sure to obtain my other course named Aerospace Engineering: Basics of Aviation Engines. You can also find this course in my profile. In this course, we talk about different types of aerospace engines, their working principles, and so on. Okay guys, now let's have a little quiz. The quiz consists of 3 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary purpose of an aircraft engine system? The correct answer is to generate thrust that propels the aircraft forward. Question 2. Which of the following engine components is responsible for extracting energy from exhaust gases to drive the compressor in a gas turbine engine? The correct answer is turbine. Question 3. What type of gas turbine engine is most commonly used in commercial aviation? The correct answer is turbofan. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about engine fuel and oil systems. See you in the next video. Bye.